In 3.2, we are going to talk about the derivative as a function. Now remember, we've already discussed how we can find the derivative. We can use that difference quotient, or you can use that limit as x approaches a of f of x minus f of a over x minus a. You can do either or. The difference quotient is usually a little more efficient. Before, we kept plugging those a's in, and the only difference here is we are going to use x instead of a to get a general function for the derivative. Now remember, the derivative is just the slope of the tangent. So we already know the derivative denotes this f prime notation, and it just stands for our difference quotient here. And so we can call that f prime. We can call that the derivative of f. We can say that it is differentiable if when we take the derivative exists at a particular a. Now there are different notations for derivatives. So you're going to see, you might see f prime, you might see y prime, you might see dy dx. What that means is I took the derivative of y in terms of the variable x. Same thing here, I took the derivative of function f in terms of the derivative f or x. We might have multiple variables, and that's why as you progress higher into calculus, they are going to specify what variable we are dealing with. And sometimes you'll see this capital D notation, sometimes you'll see the little d notation. Some notations going to be used more often than others. We're mostly going to use this until we get to something called implicit differentiation, and if we do something called differentials, we would use that dx notation. Sometimes there are spots on a graph where we are not differentiable. If you have a corner of a graph, absolute values have this happen. We found that the limit from one direction was no one number, the limit from another direction was another number. It doesn't exist. How can we differentiate it there? If it's discontinuous, obviously, and it might be undefined just because we have a vertical slope of our tangent line. The slope of the tangent is the derivative. So if we have a vertical tangent line, then that slope is undefined. So the derivative would be undefined. So let's practice finding the derivative. So we're going to use the difference quotient. We're going to do the derivative. We're going to keep x in there, and we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. So you're going to have to know that formula by heart. Okay, so the first thing we're going to do is we're going to replace x plus h and x in that formula. Remember, that's f of x. F of x plus h is just the square root of x plus h. So the derivative is going to be the limit as h approaches 0. I said it, but didn't write it. Of f of x plus h minus f of x all over h. Now we had seen limits like this. If you plugged in h being 0, you get 0 over 0. We know that there is something we can do to manipulate the algebra. To manipulate the algebra, get in the habit of surrounding any place with more than one term with parentheses, and we are going to multiply by the conjugate. Now the conjugate only changes the sign we see right there. Now, when we multiply by the conjugate on the top, that's the one we have to fix. So it's just going to be the difference of squares. So it's going to be the first term squared minus the second term squared. And the bottom, don't worry about it. Leave that conjugate just sit there. Because the thing that's causing the problem is we can't divide by 0, and we're trying to approach that. So if we can get rid of that 0, you're always looking to get rid of the h. So what's nice is we have a positive x and a negative x that cancels out. So we get h over h times the square root of x plus h plus the square root of x. We're still not ready to take the limit yet because we still have 0 over 0 causing an issue. But h is divisible by h, and we are left with a 1 in our numerator. And you'll notice that it left the conjugate behind. That's why worry about multiplying through by that conjugate, or because we don't want to get rid of the conjugate, we want to get rid of the h. And so now it's possible to plug in 0 for our h. So the only thing that's going to become 0 is this spot right here. And it's a continuous spot of the function. It's perfectly fine with this new revised version. So we get 1 over the square root of x plus the square root of x. That's 2 of those, so it's 1 over 2 square root of x. So the derivative of the square root of x is 1 over 2 times the square root of x. Now, what will that allow us to do? Well, if we want to find the slope of our tangent when x equals 4, you plug in 4. Slope of the tangent when x equals 0, we can plug in 0. Now, that's one where we have a problem. It is an undefined slope right there, and we'll address that when we need to. Let's look at this one. So let's write down our formula. The derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's do f of x plus h right here. So remember, that's going to be x plus h squared minus 2 times x plus h. We have a lot of math that we need to do to make that work. So if we do x plus h squared, we get x squared plus 2xh plus h squared. I'm going to distribute the negative 2, and there's no like terms, so that's just f of x plus h. So the derivative, which will give us the slope of our tangent lines, is going to be the limit as h approaches 0 of f of x plus h, which is that whole thing. So it's just x squared plus 2xh plus h squared minus 2x minus 2h minus off our function, minus the f of x. So put that in parentheses. Now, if at this time we tried to plug in 0, we would get 0 over 0. That's always going to happen until you manipulate the function. So if you think about the fact that this is going to become a negative x squared plus 2x, we end up having an x squared and a negative x squared. We end up having a positive 2x and a negative 2x. And then everything else that's left has an h in it. Look, that has an h in it, h in it, h in it. So everything else that remains in our problem will have an h, which is great. So we have 2xh plus h squared minus 2h all over h. And now we are allowed to plug in, or I'm sorry, divide by h every term. Now we got to do it to every term. So this gets divided by h, divided by h, divided by h. And we are left with 2x plus h minus 2. And now if we plug in 0, we find that the derivative is 2x minus 2. So that is an example of a polynomial. So we've seen a square root, we had to use the conjugate. We've seen a polynomial, we have to really multiply that out and cancel out some terms. Now here we have a graph of a function, and it says to graph the derivative. Okay. So let's put on every single time our tangent slope would be 0. That would mean that we have a horizontal tangent, and that means that the derivative, the slope of our tangents, would be 0. So let's put those on. Next, we know that this part of our graph, the slopes are positive because our graph is going uphill. So right here, our graph would be positive. Now, how positive is it going to be? I don't know. I mean, you can guesstimate. Like here's a little less, and then here's a little more, and then here's a little more, and then it comes back down again. But just make a guesstimate. Oh, okay. And then in this section of the graph, our slopes are negative. See our tangent slopes, negative, because it's decreasing. Tangent slopes are negative because it's decreasing. So those would have to be under the graph. And so our derivative would look something like that. Now, I don't need it to be super accurate. I just need you to hit the zeros in the right spot. Where it's increasing, it should be above the x-axis. Where it's decreasing, it should be below. We'll worry about more accuracy in the future. Let me just see how many more types we've got. Let's come back to that one. Since we've already done a square root, we haven't done a fraction yet. So let's do this fractional one. So the main ones you're going to end up seeing are square roots, polynomials, and rational functions like this one. So let's first write out what in the heck is f of x plus h. Well, that's going to be 1 minus x plus h in parentheses over 2 plus x plus h in parentheses, which becomes 1 minus x minus h, 2 plus x plus h. Okay, so that's f of x plus h. So remember, the limit as h approaches 0 of f of x plus h minus f of x all over h is our derivative. So let's place those things where it goes. So f of x plus h goes first. So 1 minus x minus h over 2 plus x plus h minus off our original function. So I'm just going to put that fraction over here and all over h. Now, if you wanted to torture yourself and if you plug 0 in, you would find that we end up getting 0 over 0. Not helpful, undefined. We have to do something. For square roots, we use the conjugates. For polynomials, we multiplied everything out as much as possible. We wanted to see everything so some terms could cancel. Here, we are going to use common denominators. So this is what I want you to do. Surround all of our fractional pieces by parentheses. Surround the entire top and the entire bottom by parentheses. And we're going to multiply by all our inner denominators. So I'm talking about this denominator and this denominator. So I'm going to multiply the top by 2 plus x plus h and 2 plus x, and the bottom by 2 plus x plus h and 2 plus x. Okay. Now the reason we're going to do that is so that we can cancel out some of our denominators. Because if I multiply this, it's going to sit on the top, but the 2x plus h's cancel. Now look what's left. We have the 1 minus x minus h and a 2 plus x. Let's write that. So I have the 1 minus x minus h and the 2 plus x. Now, if I multiply this on the top, it would go on the top. The 2 plus x's would cancel. We would have 1 minus x. We would have 2 plus x plus h. Now there's a minus 1 minus x, 2 plus x plus h. Now, if we multiply here, don't do it. Don't torture yourself. Who cares? The only thing we want to try to get rid of is that h. So just leave that big old list. The only one we're going to end up usually multiplying out is the top. Okay, so I kind of gave you a clue as to what we're going to do next. We are going to multiply out the top list of things. We're just going to list it. It's going to be a big old list, so you've got to be really careful. And if you catch me making a mistake, let me know. Okay, so we're going to get 2 plus x minus 2x minus x squared minus 2h minus hx. Now all I did was take this one twice, that one twice, and that one twice. I just distributed. Okay, now let's think about this piece here as negative 1 plus x, because if I distribute that negative in, and then let's distribute negative 1 plus x to both of those, or all three of those. Okay, so if I distribute in negative 1, I get negative 2, negative x, negative h. If I distribute in a positive x, I get positive 2x plus x squared plus xh. And now I'm just going to write the bottom. Don't touch the bottom. Leave it alone, leave it alone, leave it alone. Okay. Now let's start finding pieces. Any pieces on top that have only x's in them should go away, or only numbers, no h's, it should go away. Okay, so let's really focus in here. There's a positive 2, there's a negative 2. Cancel them out. There's a positive x, there's a negative x. Cancel them out. There's a negative 2x, there's a positive 2x. Cancel them out. There's a negative x squared, there's a positive x squared. Cancel them out. Now everything else we see here has an h in it, but one of them actually does cancel out. We've got this negative hx and this positive hx. They're the same, or opposites. Cancel them out. So the only thing left in our numerator is a negative 2h, and a negative 1h is negative 3h's. Guess what? I can cancel out the h's, and that's what I wanted to be able to do. So I get the limit as h approaches 0 of negative 3 over 2 plus x plus h and 2 plus x. Okay, now if we plug in 0, the only thing that becomes 0 is your h. So we end up with a derivative of negative 3 over 2 plus x times 2 plus x, which is negative 3 over 2 plus x squared. So we've seen a square root, we've seen a polynomial, and now we have seen a fraction. So that's your derivative. So if we wanted to find the slope of any tangent to the f of x equation, we could find the slopes very easily. Just plug into that formula. Actually, let's skip that. Some facts that are important is if we have a position function, which we will usually call s, if we want the velocity that that thing is traveling, we're just going to take that derivative. And if we take the derivative one more time, then we get the acceleration function. So this is really important as far as some applications for the first derivative and the second derivative. So if we have the position, take the derivative once, you get the velocity function. You could write that as v of t or s prime. Take the derivative again, you get the acceleration function. So the first derivative of the velocity function is the acceleration, or the second derivative of the position function is also the acceleration. So let's look at this example. So the position function is given by s of t. Find the function that describes its acceleration in time t. Now, I'm going to save us time, I'm going to pretend like we've done the limit as h approaches 0 and we've found our velocity function. Let me tell you what it is. It's going to be 6t minus 4. Okay, so we found the velocity function. And then once we've done it once, if you do it one more time, you're going to get the acceleration function. So let's take and find the acceleration function by doing the limit as h approaches 0 of v of t plus h minus v sub t all over h. So t plus h, the velocity at t plus h is just 6 times t plus h minus 4. And then minus our original function, we would minus both pieces. So change both pieces signs. And the t's go away. The 4's go away. We should only be left with something with an h in it so that we can divide off the h. And the limit as h approaches 0 of the constant 6 is 6. So our acceleration is a constant 6. It never changes. So if you know the position function and you take the derivative once, you get the velocity function. That's what this is. And if you take the velocity function's derivative, that's what this is. That is your acceleration equation. So when it's a constant like that, that means the acceleration is always 6. It never changes. And that's that example. Here is the 3-2 homework. Not a lot to do. We have some polynomials and some fractions. And I would like you to add one more, a number 12. I want you to find the derivative of x, the square root of x minus 2. So then we have some regular polynomials, some fractions, and a square root. Okay, so that is 3.2.